Here's a warm-up problem. Consider the claim, if n is an odd integer, then n squared is odd. So to start this lesson, please pause the video in a moment and try these two questions. First, create a few examples, concrete examples, to convince yourself that the claim we see here is true. And second, write a clear, precise, convincing, amazing, perfect, awesome argument explaining why the claim is true. So now please pause the video and think about these two questions. Now let's start with part A. So here is my example. We can certainly make many more, but with n equal to 7, we see that 7 is odd. And then when we square it, n squared is 49, which is also odd. Here's one of many examples we could make. And I really can't emphasize this enough. The value of concrete examples. This is really, really important, and I'll keep emphasizing it throughout this course. So once again, concrete examples are really, really important to understand a mathematical statement. So in the next slide, we'll start talking about why this claim is true. Now, before we dig into why this claim is true, let's dig in a little bit into what we mean by an odd integer. And I think we know what it means from experience, but let's be more precise about it. So once again, let's look at some examples. So, for example, we know that 7 is odd because 7 can be written as 2 times 3 plus 1. How about 213? Well, we know 213 is odd because 213 can be written as 2 times 106, that's 212, plus 1. How about negative integers? So negative 1081. Well, that's odd because negative 1081 can be written as 2 times 500, negative 541 plus 1. And so we see that all these odd integers have the form 2 times another integer plus 1. And that's going to be our definition of an odd integer. So here's our definition. We say that an integer n is odd when we can write it as 2 times k plus 1 for some integer k. And so in our examples, this would be our n would be 7, and k would be 3. Or n would be 213, k would be 106. Or n would be 1081, and in this case, k would be negative 541. And so that's what we mean by an odd integer. Now, when we talk about odd, naturally we can also talk about even. And we say that an integer n is even when we can write it as n equals 2 times k for some integer k. So those are going to be our definitions of odd and even. And now we're ready for our very first proof of this course. Now, I should first mention that our claim, if n is an odd integer, then n squared is odd. This is an example of what's called an implication, which is a fancy way of saying it's an if-then type of a statement. An if-then statement is called an implication. And many of the statements we'll prove in this class will be an implication. And so here's our very first example. Now, implication has two parts, the if part and the then part. The if part, in this example, it's n is an odd integer. An if part is known as the hypothesis of an implication. And the then part, in our example, n squared is odd, That's known as the conclusion of an implication. So again, if part is the hypothesis, the then part is the conclusion. And here is how in mathematics we prove an implication. We assume, so it's a two-step process. Step one, assume that our hypothesis is true. That's typically the easier step. And the more challenging step is step two. We have to show that the conclusion is true. And so that's our strategy for proving an implication. So with that in hand, let's write down our very first proof. So once again, step one, we have to assume that our hypothesis is true. Our hypothesis is n is an odd integer. So let's start by assuming that. Assume that n is an odd integer. So we can already put a check mark next to our very first step. Complete. Now, the next step is we're going to show that the conclusion is true. And so our very last step of the proof should be n squared is odd. And so typically I like to just write down at the very bottom, that's our last sentence. Thus, n squared is odd. So our first step is assuming the hypothesis, assume that n is an odd integer, and our last step is our conclusion. Thus, n squared is odd. And now we have to progress in a logical manner from our hypothesis all the way down to our conclusion. And so let's write that down. Now, we're assuming that n is an odd integer. And we just saw that n being an odd integer means we can write it as 2 times another integer plus 1. So let's recall that definition and write it down. So we can say then n can be written as 2 times k plus 1 for some integer k. So that's our definition of an odd integer. Some integer k. Now, what's our next step? And I think with proof writing, one of the most difficult things is knowing what that next step should be. And oftentimes I like to look ahead at the end of our proof. Say, oh, okay, we're supposed to say something about n squared. In particular, we're supposed to show that n squared is odd. And so that gives us a bit of a hint that perhaps we should find out what n squared is. And so let's go ahead and do that. So we could say hence, this is n. So when we square it, n squared is equal to 2k plus 1 times 2k plus 1. That's n squared. And let's multiply that out. So we get 2k times 2k, 4k squared plus 2k plus another 2k, 4k plus 1. Now, looking ahead once again, we're supposed to show that n squared is odd. That's our goal. We're supposed to show that n squared is odd. That means we need to take n squared right here, and we need to write it in the form of 2 times another integer plus 1. So can we write this as 2 times another integer plus 1? And indeed we can, because if we have factor 2 out of that portion, we get 2 times 2k squared plus 2k. And then we have the plus 1 plus 1. And so we've just written n squared as 2 times another integer plus 1. And to make that extra clear, we can also write comma where 2k squared plus 2k is an integer. So that's just being extra clear about our work. And thus, we can say that n squared is odd. And that's the end of our proof. And so once again, I like to highlight the key points here. We always begin in an implication by assuming the hypothesis. Our last step is the conclusion, namely n squared is odd. We began by translating what it means for n to be an odd integer. And then we looked ahead and said, oh, okay, we need to say something about n squared. We computed n squared, and then we showed that it's an odd integer because n squared is 2 times another integer plus 1. And that's the end of our first proof. Now please pause the video and work on day 1 classwork, and we will review some of the problems afterwards. Let's start by discussing problems 2 and 3 from the classwork. Problem 2 asked you to prove the following implication. If n is an integer, then n squared plus n is even. And for this particular proof, we use a technique called proof by cases. So briefly, we consider both cases where n is odd, and then show that n squared plus n is even. And then also n is even, and show that n squared plus n is even. So for the details of that proof, please take a look at chapter 1 reading. But now let's put our focus on problem 3, which asked, if n squared is odd, then n is odd. And so let's begin by identifying the hypothesis. N squared is odd, and n is odd. And let's see what happens if we try to prove it just like we did our very first proof. So we begin by assuming our hypothesis. So assume that n squared is odd. Is odd. And then at the very bottom, let's write down our conclusion. So that's n is odd. So we can say thus, n is odd. Odd. Now this is looking similar to our earlier proof. Well, we're assuming n squared is odd. So we can write down what n squared looks like. So we can say then, recalling our definition of an odd integer is 2k plus 1. So we can say n squared is equal to 2k plus 1 for some integer k. For some integer k. So far, so good. Now, what's our next step? Well, let's look ahead. Now, this time we're supposed to say something about n. We know something about n squared, namely it's 2k plus 1. And we're supposed to say something about n. So let's see. That means, hence, what does n look like? Well, if n squared is 2k plus 1, then n must be the square root of 2k plus 1. Yikes. So this is a bit of a problem. Square roots are a little bit more challenging to deal with. We don't even know if square root of 2k plus 1 is an integer or not, let alone being odd. And so we're in a bit of a conundrum. And so for this particular proof, we need an alternate approach. And that's what we're going to discuss in the next slide. Now, before we can talk about an alternate proof approach to problem number 3, let's go back and talk about problem number 1, which asked which of these statements are true. So let's go through them. If I live in Tokyo, then I live in Japan. Well, that's a true statement because Tokyo is a city inside Japan. It's the capital of Japan, in fact. Now, what about part B? If I live in Japan, then I live in Tokyo. Now, that's false. For example, I grew up in Osaka, Japan. So I did live in Japan, but I did not live in Tokyo. I lived in Osaka. So that statement is false. What about part C? If I don't live in Tokyo, well, I certainly didn't. I lived in Osaka. Then I don't live in Japan. Well, that's not true. Once again, I lived in Osaka, so I didn't live in Tokyo, but I still lived in Japan because that was a different city in Japan. So statement C is false. How about statement D? If I don't live in Japan, so I'm outside of Japan, then I don't live in Tokyo. Well, that's certainly correct. In order to live in Tokyo, I have to certainly be in Japan. So if I'm not in Japan, then I am certainly not in Tokyo. And so these are 4 slightly different but related implications. And let's focus on, for now, implications A and D, which both happen to be true. And for simplicity, I'm going to introduce variables. So we're going to let T be the statement, I live in Tokyo. And we're going to let J be the statement, I live in Japan. And so if I use those symbols, then we can rewrite the implication in part A as if T, then J, right? If I live in Tokyo, which is T, then I live in Japan, which is J. So implication A can be written as if T, then J. Now, what about implication D? If I don't live in Japan, then I don't live in Tokyo. Now, that can be written as if, now the if part and the then part got swapped and also negated. So if not J, then not T. And so in order to obtain implication D from implication A, we swapped the hypothesis and the conclusion, and we negated both of them by putting a not in front. Well, so what? Well, first, implications A and D are what are called contrapositives of each other. We swap and negate. And the same can be said about implications B and C. We swap and negate to obtain one from the other. Now, continuing the theme of so what? Well, the upside to these contrapositive relationships is that contrapositives are equivalent. In other words, statements A and D are saying the same thing in 2 different ways. And therefore, if one of them is true, the other one has to be true as well. Or if one of them is false, the other one has to be false as well. That was the case of B and C. And this key right here, namely that the contrapositives are equivalent, that's what we're going to utilize to prove the statement in problem 3 in the worksheet. So that's the key thing here. Contrapositives are equivalent, that they're either both true or both false. So back to problem 3 from the worksheet. We had to prove the following. If n squared is odd, then n is odd. But as we saw, it's hard to prove this implication directly. When we tried to prove it directly, meaning assuming the hypothesis and trying to prove the conclusion, we ran into square roots, which is, well, we like to avoid square roots if possible. So we couldn't prove it directly. Instead, we can prove it's contrapositive. Remember, contrapositives are equivalent. So if we can prove the contrapositive of this statement, then it's the same as proving the original statement. So it has the same impact, if you will. Now, what's the contrapositive of this statement? Well, remember, we swap the hypothesis and the conclusion, and we negate them. So the contrapositive becomes, if n is not odd, then n squared is not odd. Now, perhaps we can restate that as if n is, well, not odd, another way of saying that is even, then n squared is even. So we have this new statement, if n is even, then n squared is even. And I'll leave that up to you to prove it, but I think you'll see that proving if n is even, then n squared is even is much more manageable than trying to prove the statement in problem 3 directly. But the upside is that proving this will allow you to say, because we just proved the contrapositive, we can also say that this statement must always be true. And so here is our proof know-how. Proving if P, then Q. So P and Q are statements like n squared is odd, n is odd. If P, then Q, proving that is the same as proving the contrapositive, namely, if not Q, then not P. And so sometimes when you see an implication and it's hard to prove it directly, try to write down its contrapositive and see if you can prove that instead. So that's the end of this lesson, and I will see you next time.